Hello, welcome to another module in this massive open online course. In this module, let us start looking at a new topic, that is the Z transform or the Z transform. All right. So we want to start looking at a new concept, that is the Z transform, which is basically, this is basically for to analyze, represent and analyze discrete time. So we have seen the the Laplace transform, which is for analyze, which is for the continuous time signals and systems. So this is to represent and analyze discrete this is to represent and analyze discrete time signals and systems. Now for a given signal xn, this is your given signal, the Z transform x of z is defined as x of z equals summation n equals minus infinity to infinity xn z raised to the power of minus n. This is the definition of the Z transform. Okay, so this is the definition of the Z transform This is the definition of the Z transform of x of n, where Z is a complex. Z is a complex number and can be represented as, in terms of its polar coordinates, that is magnitude and phase, as r e to the power of j omega. This is the polar coordinate representation. Polar coordinate representation where r equals the magnitude, correct, the magnitude of z, and omega equals the phase or the angle of the complex numbers. Alright, so this is a Z transform which is used to represent and analyze discrete time signals and systems. The Z transform of the signal x of n is given by summation n equals minus infinity to infinity x n z raised to the power of minus n, where z is a complex number. Okay, all right. And then this is also represented as follows, that is x of n and x of z follow a signal Z transform pair. Okay, so these form a Z transform pair. Okay, so these form a Z transform pair. Now similar to the Laplace transform, one can also define a region of convergence for the Z transform region of convergence is basically range of values for which the Z transform convergence. The region of convergence or the ROC is simply range of values for which range of values for which the Z transform converges. Okay. For instance, consider x of n equals a raised to the power of un, where un is the discrete unit step function, that is un equals 1 if n is greater than or equal to 0 and equals 0 otherwise. So, we are considering signal xn, which is a raised to the power of n un. Okay. Now, the Z transform of this signal x of z equals summation n equals minus infinity to infinity a raised to n un z raised to minus n, which is un is non-zero only for n greater than equal to 0, and this is therefore equals n equals 0 to infinity a raised to n z raised to the power of minus n, which is summation n equals 0 to infinity a z inverse raised to the power of minus n, which is basically 1 over 1 minus a z inverse, but this converges only if magnitude, this sum converges, infinite sum converges only if magnitude a z inverse less than 1, which implies that your magnitude a must be less than magnitude z, or if magnitude a must be greater, magnitude z must be greater than magnitude a. And this is basically your ROC. This is the region of convergence for this Z transform. So, a raised to power n un, the signal has Z transform 1 over 1 minus a z inverse. However, the Z transform converges only if magnitude of Z is greater than the magnitude of a. Okay. Let us consider a to be a real quantity less than 1, consider 0 less than a less than 1, then we can plot the ROC. So, now if you look at this z over z minus a, look at this, x of z equals z over z minus a, this has a 0, that is root of the numerator at z equal to 0, and this has a pole at, that is root of the denominator, pole at z equal to a, and I can plot this in the z plane. I can plot this. Okay. We are assuming that magnitude of a. So, let us say this is a, this is the unit circle, that is with magnitude represents quantities of magnitude 1, this is 0, okay, and the region of convergence is, so this is the z plane, you can think of this as the real part of z, this is the imaginary part of z, imaginary part of z, and the region of convergence is all values of z such that magnitude of z is greater than a, which means basically covers all these, the entire circle excluding. So, this is basically your ROC, that is magnitude z greater than a, okay, and this is termed as your z plane. On the x axis we have the real part of z, on the y axis we have the imaginary part of z, and we are plotting all values of z where the ROC, where the z transform converges. This is known as the region of convergence, and that basically includes all values of z such that magnitude of z, all values of z such that the magnitude of z is greater than a, that is basically all values of z on the z plane which lie outside this circle, correct, this constant modulus circle which represents all quantities which are magnitude of z equal to a. Okay, so that is the region of convergence. Okay. Consider now a slightly different signal. This is what is, this is a n u minus n minus 1, that is basically implies equal to a n for n plus 1 greater than or equal to 0, which means n less than or equal to minus 1 equals 0 otherwise. So, this is what is known as a left handed signal, remember, similar to your continuous time, because it is equal to 0 for t greater, that is n greater than or equal to 0. So, this is basically your left handed signal. Okay, this is a left handed signal. Now, if you look at the z transform of this, x of z is summation n equal to minus infinity to infinity u n minus n minus 1 z raised to minus n. Now, this is non-zero only for n less than or equal to minus 1. So, this is n equals minus infinity to minus 1 a raised to n z raised to the power of minus n. Now, set m equals minus n, change the index, then the z transform x of z becomes summation n goes from minus infinity to minus 1, m goes from 1 to infinity, n equals minus m equals minus n. So, this will be a raised to minus m z raised to m, which is basically summation m equals minus infinity to infinity a inverse z raised to the power of m, which is basically a inverse z divided by 1 minus a inverse z, but this converges only if a inverse z, this quantity is strictly, magnitude is less than 1. Implies, this implies magnitude of z less than magnitude of a. So, the x of z, and which is equal to, and now you can simplify this, you can see that this is clearly equal to, let me just consider a slight modification. Let us consider this signal minus a raised to minus n u minus n. So, this will be minus, I will have a minus sign everywhere. So, this will be minus and this will be again minus sign and this will be minus sign, and you can see if you simplify this, you will have x of z equals minus a inverse z by 1 minus a inverse z, which is equal to minus 1 divided by a z inverse minus 1, which is equal to 1 by 1 minus a z inverse, which is equal to 1 by 1 minus a z inverse, and you can also write this as equal to z by z minus a. And in fact, the previous one also you can write this as 1 over 1 minus a z inverse, multiplying numerator and denominator by z, this becomes z over z minus a. So, you can see both of them are equal to z over z minus a. However, the previous one has an ROC magnitude of z greater than magnitude of a. However, this has an ROC magnitude of z less than magnitude of a. So, we have the same z transform x of z equals 1 over 1 minus a z inverse, but with different ROCs, that is magnitude z less than magnitude of a for this right handed signal. So, for this signal x of n equals, let me just write this again, x of n equals minus a raised to the power of n minus u of minus n minus 1, also has the z transform z over z minus a, but the ROC is magnitude z less than magnitude a, and therefore, the ROC of this left handed signal is magnitude z is less than magnitude a, and therefore, both the signals have the same z transform, that is a raised to n u n and minus a raised to n u of minus n minus 1 have the same z transform z over z minus a, but the ROCs, the regions of convergence, are completely different. Therefore, two different signals can have the same z transform, but different regions of convergence. So, to specify the signal accurately, correct, to specify the signal uniquely along with the z transform, the ROC also has to be specified, otherwise the z transform is incomplete. Okay. So, the ROC of this signal looks like, again let us consider 0 less than a less than 1, that is this circle of amplitude a lies inside the unit circle. So, this and the region of convergence is this. The region lying inside the interior of the circle, magnitude of z equal to, so this circle is magnitude of z equal to magnitude of a, and this is the interior of the circle, this is the unit circle. Okay. So, this is also termed as the unit circle, and this is of course the z plane, this is the real part of z and this is the imaginary part of z, real part of z and the imaginary part of z. Therefore, what you can see is, therefore, what you can see is x n equals a n u n has the z transform z over z minus a, and x n equals minus a n, that is a left handed signal u minus n minus 1, also has the same z transform z over z minus a, but the ROC of this, ROC of the first one is magnitude of z greater than magnitude of a, ROC of the second one is magnitude of z less than the magnitude of a. So, same z transform, different signals have same z, the same expression for the z transform, but different ROCs. Different regions of convergence implies that to uniquely characterize the fully characterize, uniquely or fully specify the signal implies to uniquely specify the signal, one has to also specify the region of convergence, otherwise the Z transform is incomplete, similar to the Laplace transform. All right. So, fully characterize the signal one has to also specify the ROC. Okay. All right, let us look at the Z transforms of some common sequences. Z transform let us start with the most common signal or the most fundamental signal, which is the unit impulse, also the discrete impulse, since we are looking at the Kronecker delta or the discrete impulse, which is equal to 1 if n equals 0 and 0 if n is not equal to 0, then x of z equals summation n equals minus infinity to infinity delta n z raised to minus n equals z raised to power minus, because this is 0, this is non-zero only when n is equal to 0 and n equal to 0, this is 1. So, this is 1 times z raised to minus 0, which is equal to 1. Okay. So, delta n, the Z transform is basically 1, this is unity. Z transform of delta n is basically unity. Okay. Let us quickly look at another common signal, that is the unit step sequence, the discrete time the unit step sequence un equals 1 for n greater than equal to 0, 0 for n less than equal n less than 0. So, x of z equals summation n equals minus infinity to infinity un z raised to the power of minus n, which is equal to, since the signal unit step is non-zero only for n greater than equal to 0 and for n greater than equal to 0, this is 1, this is summation n equals 0 to infinity z raised to minus n, which is 1 over 1 minus z inverse, which you could have as well obtained by setting a equal to 1 in the earlier expression, a raised to n un, and the ROC is magnitude of z greater than magnitude of a, which is equal to 1. So, magnitude of z has to be strictly greater than 1. This is the ROC or the region of convergence. So, the unit step signal un, unit step signal un has the Z transform un is 1 over 1 minus Z inverse, all right. So, that is a Z and remember the ROC, one has to also specify the ROC. ROC is magnitude of Z greater than 1, and here the ROC, in fact, if you look at the unit impulse, the ROC is in fact all values of Z, probably with the exception of Z equal to 0 and Z equal to infinity. In fact, the ROC is 0 less than any value of Z. Okay. So, this is the this is the ROC, that is any value of z converges for any value of z, okay, except at z equal to 0 or z equal to infinity, okay. So, or z equal to infinity, this converges for all values of z. All right. So, with this we will stop this module and continue our discussion on the Z transform further in the subsequent modules. Thank you very much.